And it's official. Welcome back, everyone. That's usually the slowest minutes to wait out. But before we get started today, any questions folks would like to begin with? Okay, well, the new thing today, definitely on the announcements are, we have our upcoming exam scheduled for just directly next Tuesday. I have to admit to you, I'm a little bit behind. I haven't actually written this exam, but my goal is by the time we come back on Thursday, that exam will be written. And for the folks that are in this section, I'll have the exam sent to the appropriate testing center, and then I'll also email you the instructions for getting your exam scheduled. For people in this section here, the assumption is that you'd be taking the exam in the classroom. So it'll almost be like a normal class. We'll start at 6 o'clock, but people will just be writing. We won't have any actual lecture material when we come back on the exam day, which is weird for the folks who might try to log in through Zoom if you're in that section there. So just keep in mind, it's going to be an off day, well, an exam day when we come back for this exam here. I should have, again, that exam written out soon, instructions sent out before we come to class on Thursday for scheduling your exam. Usually I try to get that in line a little bit sooner, but a bit behind on this class. Other things that are new on the Moodle website are the coverage of the exam is going to extend to the concepts in chapters 1 and chapters 2. And just a reminder, there's going to be no computations that you have to do through RStudio. At most, you might need to do some computations through a basic scientific calculator, but probably not on these chapters here. This is more for exam 2, exam 3. Nonetheless, I'd still encourage you to bring a hand calculator just to get in that pattern so you don't forget on the later exams coming up. Should pause right there. Any questions so far that came up about the upcoming exam?
Yeah, I'm sorry. I tuned in a little late. When is the exam?
It's going to be held on Tuesday next week, so directly a week away from today.
Okay, thank you.
Yeah, absolutely. Well, other things to mention on this exam is it is closed book and closed notes, and I'm going to be attaching a formula sheet to every exam. But I really didn't have too much to put onto this as a formula sheet. So this is what it looks like. This is the real sheet that's going to be attached as a last page on the exam. And for this portion right here, there's a great question in class. This is mainly here for the sake of just completeness and writing out what the statistics X bar is defined as a formula. You won't actually be working with these directly on the real exam 1. So again, this is really just here for the sake of completeness more than anything. The major value in this table is telling the difference between the statistic and the parameter and the typical symbol used for both. So that's the major purpose of that here. So this will be the real formula sheet attached to the exam. And as far as the sample exams go, I have 2 different versions. Version 1 is the same problems that we've solved converted into worksheets. So if you open this up, here's what it looks like. We did solve this problem, but these problems are still challenging even if you've solved them on the first week of class. It's probably a good one to come back to. And from a section by section basis, these are essentially all the problems that we looked at. If a problem has been removed, then it's my way of saying I didn't feel like it really works great on the exam. So notice that on this section, chapter 2, I have example 3 on here, then it jumps to example 5. Again, that's my way of saying these are the major ones to really take a look at for great exam questions. And because that's kind of redundant, these are the same problems we solved, I have a second version right here. These are fresh exercises that I wrote over the weekend, so I'm still a bit behind on posting the solutions. My goal is to have these solutions posted before we get into the weekend, so that'll be still a useful resource for studying. But this one goes essentially the same kind of way. If you look at this, it's a bunch of worksheets, a little bit better space has been formatted into it. And same similar kind of problems that we solved in chapter 1 that you solved in your chapter 1 homework assignments as well. So it's almost as if we've done this problem number 1 3 different ways. In the lecture, as a homework problem, and it's available in the second sample exam as well. Eli asks, will the exam be taken in class? Well, that kind of just depends on which section you're in. That's where things get really complicated for this class. If you're in section 3, then you'd be taking the exam in person in the classroom, down here in Idaho Falls. But for section 33, I'll be sending the exams out to the Wright Testing Center the Pocatello Testing Center for most is what works. For a few people, the Idaho Falls Testing Center was actually the closer one. Once I have that sent out, I'll directly email everyone in this section of the class the instructions for scheduling your exam. So if you're in that section, you'd be taking it presumably in the Pocatello Testing Center or possibly even the Idaho Falls Testing Center. Does that make sense there with that question?
I do have a follow-up. Is it
Yeah, go ahead.
possible if I'm in the section that is set to take it in the testing center, am I allowed to show up in person?
Yeah, absolutely. So if you were here in person to take that exam, you should be all fine. One
Okay.
thing I should note here is just as a personal reminder for me, the only thing that could ever go wrong is I run out of exams, right? But I have a workaround. I will just print extra exams. If I can spell that word, there we go. And that'll be my catch on that. So yeah, that should be just fine. If you've been scheduled to take it, even in the Pocatello Testing Center, but just something weird happens and you happen to be in Idaho Falls on this campus, you decide why not just take it in the classroom, I'm not opposed to that. I'll just have to be a little bit more sure I have extra exams, but you know, I actually print extra of those anyways because I use the leftovers as scratch paper. Don't tell the boss, but that should work out just fine. Other questions so far? Okay, probably more questions will come up as we come back on Thursday's class. I'll be happy to take any questions that do come up. When we're on Thursday's class, we'll probably be working on sampling distributions, but whichever questions folks would like to discuss as it pertains to this exam content here, I'd be happy to discuss it. So if we end up having a mini review on Thursday's class, it'll be student directed. It has to be questions that you ask, but really at the start of any class, I do accept questions. And I would understand when we come back on Thursday of this week, that's a pivotal week going into an examination next Tuesday. I'm very happy to take lots of questions if folks have them. Well, let's see here. Just making sure I remember to say everything. Any questions at the moment about the exam? Okay, well, the major idea with all these exams are they're highly concept oriented. So taking a look at the version 1 or the version 2 gives you a really good feel of what these real exam questions are going to look like. And I'm not going to try to go out of scope of what we did in class, what you did on your assignments. And so when I do write this exam, again, I'm probably writing on Wednesday, that's my bigger prep day. I do take another look at this document, as well as assignment 2, assignment 1, and I make sure my problems actually match up, that nothing on there goes beyond what we actually did as a class. But aside from that, our schedule is pretty tight in this class, so we still are going to work towards chapter 11, chapter 13 this week, but these are going to be contents that ends up on the second exam. And when we go down to exam 2 over here, it's just going to be a complete rehash of what we did on exam 1. We'll have the content, several versions of sample exams, a more involved formula sheet because there'll be more stuff to have on exam 2 versus exam 1 where we're just getting started. But all this is just going to repeat on a week by week basis, exam by exam basis. So where we're at right now is chapter 11. Chapter 11 is dealing with the normal distributions, and we'll do a couple more computations on modeling data by this distribution right here. Really, though, the purpose of the normal distributions in our class seems kind of strange. This is about statistical methods. Well, really about inferential statistics. So the usefulness of the normal distribution is not as much what we're doing in here. It's all about what goes on in chapter 13, sampling distributions. In a very odd way, the normal distribution can come up naturally through a theorem called the central limit theorem. It's a provable mathematical fact, but this is one of those extremely deep results of probability theory, analysis theory as well, that it could take a whole book like this big to show the full start to finish proof of a theorem like that one. It's extremely abstract, but we'll see exactly how it goes through visualizations, simulations through RStudio itself to get a feel for it. So chapter 13 is the rough one for the entire course, but the assignment is not going to ask the most abstract questions out of it. The hard thing about chapter 13 is really just understanding what's going on. So that's one we're going to take some extra time on. But first, we have to understand the normal distributions a little bit more just through some routine computations. So we're jumping back to example 3. Where do we end up? Right about here. So here's our example 3. Any questions at all, folks, before we start working through this one? Okay, just a reminder on the context of what was going on here. This was a study from a while ago, 1993, where they were making a setup. Imagine maybe you're in driver's education and you have a fake steering wheel and something in front of you that could indicate a car right in front of you. They were looking at the reaction time to a brake signal from a standard brake light. And from this study, they determined that their data could be modeled through a normal distribution. So it must have been symmetric data, mound shape. The mean of their data is 1.25 seconds, and the standard deviation was 0.46 seconds. And these are true statistics. They came from observations in the study. We're going to call them parameters only because now we're doing a different kind of thing, mathematical modeling. We're trying to model the data that they had using these two values and considering them now to be parameters for the entire population, which would be presumably anyone who has a license to drive and can drive normally. So we summarized all this information in these last 2 paragraphs here by saying X, read the definition above, so reaction time to a brake light is modeled by the normal distribution, or that tilde is just another way to say is distributed as, normally with a mean of 1.25 seconds. So our parameter mu always goes here, and our parameter sigma always goes here. So standard deviation, 0.46 seconds. Our first computation was to find the probability X is between those 2 values. And, let's redo it in RStudio just to see how it goes. I guess I forget that RStudio remembers what I typed in. To implement these kind of probability computations, you could just type them out down here in the console, and it works just fine. So type out your syntax and it will work just as before. But usually if you have a multi-part problem based off just one model that you're using repeatedly, it's a good idea to just define the model parameters here. Let's insert something new into the script. The hash is just a way to put it in a comment. So this whole region, all the white space to the right over here on this entire row, is RStudio just skipping over it. This is for us to make some notes on our syntax. All I want to say is that this is part A. So part A, by probability X is between 1.75 and 1.00, we use the p-norm function. This accumulated the area to the left of the normal distribution without stopping. It went left forever. That gives us too much area because we had to stop right at, right at 1 second. So this is taking out the excess area right here. So anytime X is in between, this is the syntax we have to use. Then running Control A, Control Enter, that's where we got the probability 0.5681 upon rounding. Any questions at all, folks, with the syntax here? Okay, and then I highlighted this part right here in purple just so I didn't forget. Honestly, that's the only reason that's highlighted. So let me undo that. I think that emphasis is just a little strong. As far as the practical interpretation goes, this is a word that we're going to see actually quite a lot in our work in this class. By a practical interpretation, we just mean a way to say what this number is meaning that is accessible to anybody, whether they've taken a statistics class or not. So we're not trying to use any special language, any special symbols whatsoever. We would just say this. If the probability came out at 0.5681, you can start by saying the probability of, and just use that figure. But usually I would probably say something more along these lines. There is a 56.81% chance that X is between 1 and 1.75. Well, that's true, but that doesn't help us, right? We need to involve the context as well, which just amounts to us looking up what X was. the reaction time to the break signal. So we'll say here, there's a 56.81% chance that the reaction time, let's say they say for an in-traffic response to a break signal, I'll abbreviate that to just reaction time to a break signal, to a break symbol, is between. The only reason we're saying is between is because X is between two different figures. So we just say what those are. Between 1 and 1.75. Again, the context comes into play because these have units. This is in seconds. So we should mention that as well down here. So the context was hit the moment we said reaction time and mentioning the units as well. Well, we did it, folks. Any questions at all with that first computation and interpretation here? Okay, well, let's try it out again then. We want next probability X greater than 2. One way to do this one is back now in our studio. Let's call this part B. We already have the right parameters loaded in. We're going to use the p-norm function as before, but we use it according to what information we see here in the probability statement. If it says X greater than 2, we begin with p-norm. Input 2 is the first thing to go inside there. Then input mu, sigma. This is just going to call back these values here. And there's no harm in just typing these in, but if I have to type in 1.25, 0.46 multiple times, there's a high chance I'm going to make a mistake somewhere and maybe move the decimal spot to the wrong spot. So defining them first just makes you more accurate and probably a little faster too. But there's one extra thing we also need here. Because of that greater than sign, we need to also input lower.tail set to false. So this will accumulate our area to the right. Without having done that, the default is that we're getting area to the left. And in a related comment we discussed last class, F works here. Our studio is going to reinterpret this and know what you meant. But there are times where that can cause some conflicts. So let's just put in false if you want to be really, really sure you're not causing any issues down the line with your syntax. Probably a small issue for our class, but it's something that if you use RStudio a lot, can come back and haunt you. So let's run this whole thing. Control A, Control Enter. Well, it ran part A as well, but we just read the last value here. It's a 0.0515. Any questions at all, folks, with that syntax so far? Okay, so we can say here, probability X greater than 2, 0.05, let me try again there, 0.0515 is a probability value. So now when we go to give the practical interpretation, pretty much the same statement here, but we'll just change the information as we see it based on the inequality around that variable. So from here, we could say there is a 5.15% chance, or again, you could say with probability 0.0515, something happens. Really up to you how you'd like to say that. I usually go with percent chance because if you're grabbing a random member of the population and you say probability and then a bunch of information, they might not get exactly what you're saying. If you say the same thing, but you said percent chance, I think people intuitively just are more receptive to understanding the meaning when you say that. So again, we're trying to give an interpretation to as wide of an audience as possible. Although there's a 5.15% chance that, look up X again, the reaction time, to a break symbol. I may call that a break light. That's probably a little bit better. Is greater than 2 seconds. And sure, that looks like a small probability, but if you're talking about a 5% chance, roughly, that's like 1 in 20. So if you imagine the person behind you, this is saying 1 in 20 times you hit the brake light, person behind you is taking, well, about over 2 seconds to respond to that. Really kind of concerning in a way when you think about it, but also keep in mind, this is just a model. Its performance and really accurately modeling what happens in reality is going to depend on what the data looked like in the first place, how well the model even fit, were the data skewed, were they highly symmetric? There's a lot going on here, and the model is not guaranteed to be perfect. So even though this might feel kind of concerning, keep in mind it's not fully accurate either. It is our best guess, though, of reality based on the model. So these are two pretty standard normal probability computations where the question was a probability value. Over here, though, it's a little bit different. Notice down in part D, we have the probability. It's been supplied. What we don't know is the K value that results in this probability down here. So that means it's a totally different kind of question. And just to emphasize, on the last problems that we did, whoa, not too sure what that was. Let me Control Z that. On the last two problems we did, with these known, we used the P norm function. Same on here. We knew the values relative to X, even though there were two values in question. So because these are known, that one and that one as well, we used P norm again, and this represents a shift. This time the value inside the probability statement is an unknown, whereas the probability itself is known. And so in this case, we will use Q norm. If you thought about how are we going to solve this function, suppose, for example, we were dealing with a function more common in calculus, like say, e to the power 5 equals 2. Well, I put in a value. Let's suppose it was with an unknown. There we go. That looks a little bit more relatable mathematically to what we have down here. If you're going to try to solve this function in a calculus setting, solve this equation rather, you would need an inverse function. The inverse function is the natural logarithm, so you just take the natural log of the left side equals the natural logarithm of the right-hand side, and you just get k is natural log 2. And it's the same story over here. This is a function in its own right. We sometimes call this the probability set function because the input to it is a whole set. The set of the numbers less than k, the set of numbers greater than 2, for example, or the set of numbers between 1 and 2. So its domain is sets. Its output is a real number between 0 and +1 inclusive. But the amazing thing about this function is that it is 2 invertible. Its inverse is Q norm. Well, P norm is hard to implement in the first place. It's an integration. Q norm is not any easier. And if you're really curious about how all these tiny little things are really working, you need a good course on probability, and then the mathematical statistics course goes into this into very high detail. But the good news is RStudio knows exactly how to do it, and it has a numerical routine which is amazingly fast even on slow hardware. So we'll just use the QNorm function to solve this one and see what we get. But this one is such a different problem from all the rest. Let's also include a little graph just to try to help out. So by a little graph, I mean just a crude sketch of the normal model in this problem. Here it is. This was n, and I've already forgot the parameter values, 1.25.46. In the center then is 1.25, since this value is always the mean, the central value, which lines up with the main peak. We want probability x less k to be exactly 0.10 in probability. And because of the less than side right here, k should be in this location, somewhere to the left. That makes this probability 0.10 refer to this region right here shaded. So our goal is to find the value of K that leads to a probability, which is an area of 0.10. Good news is, again, our studio is really rapid at this. Here's how it goes. Let's call this part C. We're using the Q-norm function because this is an inverse problem in a literal mathematical sense. We need the inverse function. So go Q-norm. Into the Q-norm function, we give the supplied probability this time, 0.10. Then go mu sigma, like from before. And because the direction is less than, this is all set up correctly. We don't have to say lower dot tail is false unless there's a greater than direction there. We'll see that in one of the next questions. So now running all this has solved this equation for K, much like taking the natural log here has solved for K. Let's see what we get. It's a value of about 0.66 seconds, which seems right from the figure here. So let's say probability x less than k equals a 0.10 immediately implies k equals, and I'm not very good at remembering those. You can use your best judgment for rounding. Usually with probabilities, we go to 4 decimal places generically. And for solving for a value on the horizontal axis here, we would probably more likely round to a couple decimal places. There's no reason to go to, say, this many decimal places for time, I would say. So let's say k equals 0.66 seconds. And now we've got it, folks. All we need to do is supply a practical interpretation to this. You know, saying that it was seconds is already a big upper hand on that. But any questions on the RStudio side of getting that function there to work? Okay, so now for our practical interpretation, here's what we'll say. Well, it kind of just goes the same, right? You could read out these statements here, this is the same as you can read out these statements right here, because we now know the value of k. So one way to say this is, you could say that there is a 10% chance that the reaction time to, I guess brake signal does make sense. I don't know why I thought that seemed weird. I'll call it a brake light again. To a brake light is, we have to say less than, then just mention the figure we found, 0.66 seconds. So if you enjoy parallelism with the way we did the practical interpretations here, really the same kind of thing on this one. But you know, there's lots of ways you can interpret this. So I want to give a second option. Anyone have a different way you'd like to say it? Well, for me, I would say kind of a fun way to say this one is looking at the probability given is small. Looking at the direction, we're on the lower end of the scale, but remembering the context, this is a scale for X, reaction times to a brake signal. So if we're looking at this lower end with just a 0.10 in area, we're looking at the 10% people with the fastest reaction times in this population. So we could say here for another interpretation to 0.66 seconds is the 10% of the population with the fastest reaction times to a brake light is, let's say, has a reaction time. This may not be the world's most grammatical sentence, but let's just keep powering through it. Has a reaction time of 0.66 seconds we shouldn't say that. It's not a single number we're really producing. We should say 0.66 seconds or less. So that's a great way to say it as well for just a different option. I think this is a pretty decent one to think about as well, because sometimes these questions aren't really stated with a probability statement. The way these questions could be stated are through the practical interpretation first. Then we have to reverse engineer what is the probability statement to know exactly what should go in for our syntax. So there's really two styles to these questions. One where you supply the interpretation, the other where you supply the probability set function right here, the probability statement. But we did finalize this question, so here's the full syntax for when you see this related type of problem in the homework as well for chapter 11. A lot lighter than the things we've done before. I think producing graphics is sometimes really, really tricky the first time you're using RStudio. But this syntax represents us using RStudio as more just a generic calculator with extra features for sure. So this is usually the nicer spot of RStudio once we get using it more and more. Well, before we go on to the next problem, there's a bit of a discussion on R syntax. We didn't do every possible version of these kinds of problems. And so if you want a one-stop shop for syntax as it relates to dealing with normal distributions, you can click on chapter 11. Click on the R syntax here. Either file works the same. And this tells you any possible computation that you might need that could come up in this course. We did, say, this one, part 2, for example, part 3, and we did part 4, but we have not done part 1 nor part 5. I believe our next exercise is going to target those next. Well, here is that same R syntax as well in the notes. Sometimes other things are in the notes like this, but I've worried it's buried. I did definitely like to put in these files down below under the notes, just so you can easily grab that information. And there we go, we're back to this. So here's all the syntax that we've been discussing. But one thing I want to do on this diagram right here is just visually show how some of the syntax really works. So let's consider this to be our probability distribution, like in the last problem. Now let's suppose you want to solve two related computations. Maybe it's probability x less -2. Another one could be probability x greater than k equals, let's say, 0.05. So these are definitely two very, very different style of questions. Over here, the probability is unknown. And over here, the value for x that leads to that probability is the unknown. And let me just throw in a horizontal axis here, just so that it's easy to look at. That's kind of tough. I should find a way to make RStudio plot that. Okay, so here's my shoddy horizontal axis. That's an axis for whatever the variable might be, x in this situation here. So now if we want probability x less -2, we would just say that this is p norm -2, your value for mu, your value for sigma. Now the graph, it would look like this. What we're finding is an area, and it would be that area up there specifically that we'd be producing when we use that syntax. So this is the p-norm function, but this one is always a little bit more vague. Let's give this one some special attention as well. If you're solving for the k value here, we'll say that k equals q norm. This value right here goes inside the q norm function right away, so 0.05. Then pass to it to mu, sigma, and then ran out of space here, but this is our syntax it's trying to duplicate, so we'll just go down a line. Notice the greater than direction. This means for this computation, it didn't come up in the problem we just solved, but it will in the next. We have to control the direction by saying lower dot tail equals false. We try to get into the habit of just writing out the whole thing, true and false, as they come up. the way we visualize this is we take that 0.05, shade like this. As now this is area equals 0.05, coming from the supplied value in the probability statement. And then wherever we find K is, it's just going to be this cutoff spot right here, so that the area directly to the right of K comes out as 0.05. So in Q norm, you're solving for the value on the horizontal axis, whereas for P norm, you have a value on the horizontal axis, you're solving for area instead in that case. So they're confusing functions because they are not in isolation. We have to consider them both at the same time. As a graph, this is the difference between the two. Well, any questions, folks, with looking at this syntax and this more of a graphic look? Oh, I have a chat. Awesome. Hay says, what is R again in front of Q norm? Oh, yeah, that's a, let me see again. Oh, that should have been a K. Thanks for spotting that. I was looking at my R too. That one was kind of poorly drawn, but that value right here was meant to be the same K as this K right here inside the probability statement. Yep, absolutely. Thanks for asking about that one. I do appreciate comments about my penmanship because if one person can't quite see what it is, then probably a lot of people can't. So never hesitate to ask for clarification. I appreciate it. Other questions at the moment? Okay, well, we have one more question so far, so we're going to give that a try. But really our bigger goal today is to explain why, even when the data looks bad like that, somehow, some way, the normal distribution is still on the table. This is a very, very weird fact about statistics, and that's the central limit theorem work that we're going to be taking a look at. But talking about the central limit theorem is unhelpful unless we're really fluent with how the normal distribution works in the first place. So that's the major takeaway of exercise 3, exercise 4, or example 3, example 4 rather. So here's another look at these same kind of information. This example says, in Rochester, New York, they average 21.9 inches of snow for the month of December. Be interesting to know how they did last December. Let's just highlight that as, usually I go for blue when it's an average or a mean. It says next, the distribution of snowfall amounts is normal. So normal distribution is available to us through that statement. And we have a standard deviation, 6.5 inches. Now this problem, again, we're just doing some mathematical modeling through the normal distribution, but it is a little bit different from even the last one we looked at. The last problem on break time reactions was actual sample data, and they just fit parameters to that to hopefully model the whole population. Here, it looks like this information is purely through historical records. And now we're just hoping that the historical records, this average, is still relevant to the next month of December in 2025. In either case, we're trying to model something that's going to physically happen in reality, snowfall in 2025, based off our best guesses. We're not saying we know the value of the parameter mu. All we're saying here is, whatever mu is, this is going to be our best guess, 21.9 inches. Then we drop that value right down here. When we go to model X, we have n right here because we were told it was distributed normally. Next, from this part of the write-up, we have a value sigma equals, let me try again on the sigma. That looked like a sideways number 6. That's a little bit better. Sigma equals 6.5 inches. That's the value that goes down in here. X itself deserves to be highlighted. Let's go with gray on that. It's going to be the amount of snowfall in Rochester in December of this year, so 2025. That way we didn't have to update the notes there. And we'll assume the probability distribution of X is accurately modeled this way. I mean, that's just an assumption. Your assumptions can be wrong, but we're going to run with it and see if that assumption is true, what conclusions we can give. So let's run through this again. Any questions first with the write-up? Okay, usually what I do if we're doing normal distribution problems, but we're on a new type of model, just wipe out what we did before, start fresh. Either look to these values for mu and sigma, or look to what you might have written on the margin of your paper. The model supplied, I typically just go here and write mu gets 21.9. Then from over here, I would just type in sig or sigma. I usually just go for sig, 6.5. The hash symbol allows you to mark up your code or your syntax as you're writing this out. All I'm doing here is just saying what part we're on, nothing fancy. And before we get too far on this, notice that there is something different about this problem. It's asking, what is the probability that Rochester will experience 10 inches of snowfall or less this year? This is the practical interpretation to whatever number we put down. So I'm not asking you to say it again. That would be really, really redundant. It's kind of the reverse of example 3. The new thing on this one is we're being asked to write down the probability statement. So let's write this in. The probability statement in this problem comes from the practical interpretation. It reads out as, what is the probability? So put in the probability set function. Rochester will experience 10 inches of snowfall or less this year. Well, that's talking about X, the amount of snowfall in Rochester in the month of December. So we'll put in X. 10 inches of snowfall will go here. But this is 10 inches of snowfall or less. So we'll go either less than. If you put less than or equals, you'll get the same value in RStudio. So that's what the probability statement would be for this problem here. We also have to find the probability. Once we place it down, we're totally done with this problem. Well, now that we've done that, come back over here. In this configuration, the input value inside the function is known, so that makes this a p-norm process. We're still getting kind of used to that dichotomy, so let me say here, this indicates use p-norm. So back into the p-norm function, we give the input value 10, pass the parameters that we already defined, use sigma, decide if we need to set lower tail false or leave it as, but if it's a less than symbol here, the default is lower.tail is true. We'll always be doing area to the left. If you ever wanted to just be hyper specific, you could always add this, lower.tail equals true, and that works out just fine. I think more often than not, people only input this parameter when there's a greater than sign here. Because the default is always true, I really didn't change anything about the computation. So if we run this here, it's telling us that there is only about a 3% chance of getting less than 10 inches of snowfall in December. So they have it way worse than us, and even in Idaho, it seems like, when you look at that information, depending on where you are in Idaho, of course. So this rounds to 0.0336. Well, any questions at all, folks, on our first computation for example 4? Okay, these go a little bit faster, so that's kind of nice in a way, because we're not being asked to write this out. That's the practical interpretation already supplied. Next one says, what is the probability Rochester will experience between 10 and 20 inches of snowfall this year? For the probability statement on that one, we would go P for probability, and then something on the inside. Anyone see what we should put inside here this time? Yeah, go ahead.
Going to be 10 is less than X, which is less than 20.
Yeah, absolutely. The statement between 10 and 20 will always imply this right here for the probability statement. Good call. Which means the syntax in RStudio is actually kind of annoying for this one. We have to call the p-norm function twice to get this to work out. So watch out for these when they occur. It's not the prettiest thing, but let's write it out. Go part B. Anytime you have in between, you always want to start at the higher value that we've listed here. So go P norm 20, U sigma for the parameters. And let's run this right here just to see what happens. This is not the right answer, so let's not record the result. But we get a probability of a 0.3850. But if we did that, that's a probability that corresponds to this statement, having strictly less than 20 inches of snowfall in that year. So it's not quite what we wanted. We want between. So let's watch as that probability drops. Let me fix the statement here. To get this part that has to be subtracted off, this extra probability, we go minus P norm. Let me try again. Not 20. If we do 20 minus 20, we're just going to get 0. I should be using the lower value, 10. Mu sigma, and this would do the job for us. So when we make that correction there, our old probability updates the correct one of, not too much difference. That's kind of interesting. 0.35. Hang on. Oh, I forget, I reread the prior parts. That's kind of hard to compare when you do it that way. Let me see if I can fix that. We read it once this way and got the 0.38. And now if I want to compare it, I don't want to run the whole thing again. I should just be running this part. So you can select with your mouse that portion, either click run or hit Control Enter. And now that's the comparison. Something went wrong here. Got to put in a value. One more try. Sigma. I just want to run this region. So ignore this. Well, this number is the same as that one. That's about what I was expecting. That took a bit to just demonstrate. The probability drops by just a little bit because once again, it was just a little bit to be probability x less 10, the 0.336. And that's what these are off by right here. So these are going together only just to show why we need the two functions right here. The second one is just subtracting the excess probability that was unneeded. So the official answer, 0.3515. Any questions with these so far, folks? Okay, well, here's our last one, part C. Then we're done with these notes, kind of a smaller chapter in a certain sense. It says, what amount of snowfall describes the 1% of worst cases for the month of December in Rochester, New York? Include the probability statement in your answer is the most annoying part about it, but it has its value. We're just getting used to seeing this two different ways. It'll be probability, X, and then something goes here, but we're guaranteeing the problem is, if they gave you a probability, even if it's written as a percentage, it's what goes on the right-hand side. We do have to fix that, write it as a decimal form. So that's the only requirement of probabilities, which we have to be careful because we give Q-norm a probability, not it as a percentage. So take that, write it in as a 0.01. And then we're all set here. But now we need a direction. The direction that goes here is going to come from really your interpretation. What does it mean to have a worst case? Would you consider that a greater than or a less than? Yeah, for people who actually live in New York, they're probably annoyed by the snow when it's really bad. So worst case would be lots of snow, like you said, which would imply greater than sign. X is going to be greater than this amazing amount of snowfall that's going to shut down the city probably, if this is really the 1% of worst cases historically. The value then we're trying to solve is K. Oh, thanks for spotting those. Ben asked, are you using significant figures or are you just rounding where it feels appropriate? pretty much rounding where it feels appropriate for these. Usually when it comes for probabilities, 4 decimal places is great generic advice. But when it comes to getting the K value down, this is where I'm pretty much just doing, as you said, using what feels appropriate. So here, I had a lot of accuracy here, but I felt that just 2 decimal places was going to be appropriate here. I won't be too specific with rounding throughout the course. So usually you can use your best judgment and be just fine. And Eli asks, would we get it wrong if we did a less than? That's a great question. Thanks for asking that, Eli, because you're thinking from the point of view of being an Idahoan who perhaps likes the snow for the extra activities you can do recreationally, the worst case is a less than right here. And if this was a real question, say on the homework assignment, and I never stipulated what the worst case would be, and it's ambiguous, you would not get it wrong. I would just see that this is your interpretation of a worst case. That means this would be a really bad homework exercise, right? I try to be more specific for actual homework exercises, exam exercises, because it's absolutely open to interpretation, like you said. Other questions at the moment? Okay, well, we're ready to solve this value here, but I noticed I forgot to add a couple bits of detail. We knew we were using p-norm on both of these cases, but what makes it p-norm is we're supplied 2 values here. 1 or 2 makes no difference, it's still p-norm. And the only reason we need a different function here is because this value k is unknown. We use q-norm. Think of q as a way to say quantiles. So it corresponds in a certain sense to saying the quartiles and things like that. So q-norm, q comes from quantiles, which is referring to you have a probability or a percentage in question. So back over here, here's how we'll call the function. Go, because of this k right here, q-norm, we were supplied a probability, so that's the first thing we give to the function, 0.01. We need to add other parameter values, mu, sigma, and this is not right, but let's run it anyway, see what happens. If you run it like this, it says K is about 6.77 inches of snow. But that can't possibly be right if we had a greater than here, thinking of worst cases, because the average is 21.9%. Our K value should actually be much bigger than that. Anyone see what the flaw is in the syntax up here? Absolutely. Because of the greater than sign right here, we require lower dot tail be set to false. Let's say that here. Use lower dot tail equals false. So fixing that syntax, here's how we can get a better figure. Lower dot tail. Set false now. And this figure, which was about 6.7 inches of snow, becomes 37 inches of snow. That's a very big difference in how much your back is going to take that after shoveling all that stuff. So this is our figure we're going to report. And in spirit of what was said earlier, I'd say rounding to 1 decimal place would make sense for these data here. Hayes says, will lower tail always be false for greater than sign? Yes, absolutely. So you notice when we had the less than sign in the prior problem, we never had to use that on example 3. So our value came out as 37.0 inches of snowfall. Other questions so far? Okay, well, we did it, folks. This is our kind of rundown on what is a normal distribution, how to work with it, and get some routine computations to come out. These will be problems that we'll see in homework, just practicing with the normal distribution. But really, the normal distribution is emphasized a lot more because of chapter 13. And notice what we've been doing all along these problems. We're talking about a variable x. X refers to the amount of snowfall. And there's no reason to expect that this function with the right value for mu, the right value of sigma, is going to give us a full picture of what really is going on in Rochester, New York for snowfall. It's just a model and its accuracy can be great or very poor. Oh, sorry for missing the chat. He says, how about for p-norm? Will lower dot tail always be used for false for a greater than sign? Yes, absolutely. So that's where we had here with the less than, we just used an ordinary mu and sigma. But when we were doing this one with a greater than sign in our syntax, we had to go lower dot tail is false in that part B. Let me see if I can zoom just right. That's kind of hard to see. But yeah, if it's a greater than sign, we will always use lower dot tail is false, like in that part B right there. If it's stuff in between, we don't use lower dot tail is false whatsoever. And if it's a less than sign, say here, that was this part A, we don't need it as well. So it's the greater than signs we're going for. The default is to accumulate area to the left, but if we want area to the right in our discussion, that's the only time we use that. Other questions at the moment? Okay, well, let's save this up here. And now we're going to do the exciting and wild work of describing an extremely deep result of analysis and probability theory so that we can use it in inferential statistics. It's really kind of weird in a way, but the good news is the harder thing that we need to do in this class, like we mentioned, is not understanding the proof to the central limit theorem and such. It's more about if you can understand what the sampling distributions really are, what it's trying to say, then you will have great use of the central limit theorem. Proving it is one whole completely different matter, unfortunately. So here's how chapter 13 starts. Looks like with a pretty big rundown on some differences of population versus parameter, the sample and the statistic. I did say that I revised these notes today, this morning. My revision is on this example here. I had an example discussing simple random samples that was here, but I felt like it wasn't very successful in past semesters. I feel like this example here, where we actually just take a simple random sample, will be way more informative of what we're trying to do. But this set of notes right here starts off with lots of definitions, mostly as just kind of a review and wrap up of things that we've seen before. Let me fix my window real quick here. So recall, we always have a huge dichotomy of things along these lines. A parameter. A parameter is going to describe the mean or standard deviation or some other kind of quantity for the entire population. So if our population is all ISU students, then the high-level administrators that work for ISU are very concerned with this parameter. And they can probably compute it because they have deep database information that is going to allow them to do so. But if you are someone external to ISU, and you're trying to research ISU, there's reasons to do that. Maybe you're trying to draw students away from ISU to your campus. You need to do some external research by selecting a sample. The reason for the sample is doing external research when you're not an administrator and you can't compute mu is cost prohibitive. But if you can contact a representative sample of 100 ISU students, then you won't know the value of mu, but you can make a highly accurate guess through the central limit theorem. The statistic is just a point estimate. We also need to know the error in that estimate to fill out that guess. But what makes this a statistic here, we're calling it X bar, is because it's just describing the sample this time, the 100 students selected. Then what those people who are external to ISU are going to do in their research is make this estimate down here, that the unknown parameter to mu, unknown to them, is approximately equal to the statistic coming from their data, X bar. But there's a lot that goes wrong here. We mentioned before that in doing this estimate, we have to describe the error in making the estimate in the very first place for it to be of really great use. Otherwise, it really is a wild guess at this point. The second thing that can go wrong is that sample could have been chosen poorly. If we're interested in the entire campus of ISU, but all 100 students came from the main campus, that's a big problem because not all students are on the main campus. Some of them are fully online, some of them are on satellite campuses, Idaho Falls, Twin Falls, Meridian, I think there's even more. So if they don't select the sample right, then not only are we not sure what the error is in this estimate, it could be just totally wrong. It could be targeting a population which they never intended to target. What we require then is a representative sample of all students in ISU. So the way they have to do that is they should take a simple random sample to make that happen. Simple random sample is really the golden standard for sampling designs, in particular with this book, because it is an introductory book. Most of the samples that we're going to look at came from simple random samples, not more convoluted sampling designs. So what do you have to have for a simple random sample? You have to make so, if it's of sample size n, then every possible set of size n has an equal chance of being selected. So in other words, if the researchers are targeting a sample size of 100, then every single possible sample of 100 ISU students has to have an equal chance of being selected in the simple random sample design. That way, we're trying to obliterate all biases if every possible sample has an equally likely chance of emerging. So that's the simple random sampling design. And again, I made a change on this example here. My thought was, we should just see how that goes. Imagine you're doing your own simple random sample, for example. We're going to take a random sample of size 20 from a population of size 1,000. We could change that number to whatever we want, but I thought 1,000 just seemed reasonable for a problem made up early in the morning. Before we give it a try, any questions so far with the setup here? Okay, well, let's go to do just that. In RStudio, we want a simple random sample. Let's first just wipe out all the syntax. Click on the little broom icon here as a quick way to remove variables, just to eliminate the chance of any kind of conflicts going on. And we'll start by resizing the window. Let me try again. Start by putting in the population. I'll call this population. Makes sense. So population gets, I need, well, 1,000 members of this population. One fast way to do this is to write 1:1000. This is just a rapid way to produce a vector that starts at the integer 1, increments to integers 2, 3, 4, ending on 1,000. So if we hit Control A, Control Enter, here's the new variable that was defined. Have to have exactly 1,000 people inside of there. And sometimes that's a little bit foggy if that's exactly 1,000 individuals. If that's a little foggy to you, maybe because this was defined in a more convoluted way, you can write length population to find out just how many observations really are in that vector. Well, we have a population now. Next thing we needed is a random sample. So to do that, we'll write sample. Makes sense, right? If you want a sample in R, you should just say sample, tell R what you want, and oftentimes you get it. It says sample and then X in the syntax above. After, well, it just disappeared. The X that you saw above there is just referring to the population we defined. So go sample, population. Next input is probably the sample size we want. Yeah, right there it says size. So just give it, we want size 20. And this does exactly what the sampling design is doing. Well, it's the best attempt using pseudo-random numbers. Pretty sophisticated, so it does a great approximation of doing a simple random sample. Good enough for deploying this into a real research situation. So hit Control A, Control Enter, and this is the sample that was selected. We have 1,000 individuals indexed by the identifier variable 1 through 1,000. So individual 219, 497, and so on through to individual 457 made it into the sample. And you can run this repeatedly. Each time it runs, the sample will always change. I mean, not always. Maybe by some sheer absurdly amazing astronomical luck, you sampled twice and got the same individuals. This happens essentially with probability 0 in practice, not exactly zero, but close enough that it is a small worry. We are almost always assuming if the population is somewhat large, even at say 100, your samples are probably different. So run this again. Oh, don't delete it. Hit Control Z if you did that. And here's the next sample. We have observation 12 made it in, 87 and other noteworthy individuals. But that's just, again, a way to implement a sampling design when you're using RStudio. So that's what a simple random sample looks like. This is kind of a strange problem because it's more of a demonstration to tie in the concept of a simple random sample. So hard to say what to really put down here. And notice I didn't say example 1. This is my way of saying not exactly a homework problem, more us just working with the definitions. Any questions at all, folks, with the simple random sample design so far? Okay, well, next thing we should take a look at is this table right here. A part of this table was put down as a formula sheet on our exam 1, but the purpose of this section right here is just a one-stop shop for looking into the related symbols we see for statistics versus parameters. We've been working quite a lot with this kind of stuff so far, but when we get back into categorical data, these are the other statistics and parameters and their definitions when we get into those. So this will be more into chapter 19. And just because we're a little bit shy on time, well, no, I think we can get through example 1. Let's give this a try. So this is also just a good place to just remind yourself of common notations. Lowercase n is always going to refer to the sample size. We don't often indicate a population size, but when we have to, it's related by saying uppercase n. We mentioned these before. Xi is going to be an ith observation in the sample. And anything associated with the population is the parameter, or called parameters. These are typically unknown. Whereas numbers associated with the sample are called statistics, and these are known values. The major idea here, the same idea that we've been hinting at, especially with this equality, well, approximately equal to symbol, is that the statistics are estimating the corresponding parameters. So X bar is approximately equal to U if we had a representative sample. A simple random sample helps us with that. Likewise, S approximates sigma, and P hat will approximate a new parameter P, which we'll describe when we get further into those sections. Well, to go along with this is a short example 1. I think this one is kind of tricky, so let's take our time with this. We do have some time to consider it fully. The write-up says, after hearing of the national result that 44% of students engage in binge drinking, defined this way, 5 or more for men, 4 or more for women, a university administrator surveys a random sample of 244 students at a college, found 96 of them admitted to binge drinking in the past week. So this problem is a little bit different because it's actually using this information right here. We don't have quantitative data whatsoever on this kind of problem. We just have a set of outcomes. The student either admitted to binge drinking, we'll call that a success later, or did not admit to binge drinking, we'll later call that a failure. So what we need to do in this problem is indicate what the statistic is. Let me try to follow my color coding. Well, the color coding broke down on this. I'm not sure what these colors are. We'll indicate what the statistic is and what the parameter is. Let me just double check I'm not changing the color coding. That'd be really jarring. Okay, we have the right color coding. First thing we can say about this is this alone is an indication of categorical data emerging the problem. Notice we don't really have a lot of information about each one of these 204 students, other than either there was a yes admitting to binge drinking or a no not admitting to binge or denying binge drinking. I'm not sure how to say that very nicely. That doesn't seem to sound accusatory, not intending to say it that way. But again, there's no information here that corresponds to any kind of unit, for example. So we're dealing with categorical data, and that's one indication there. So that means the parameter would be P. Let's say here, parameter equals P. It's going to be the proportion of the population of successes. And a success in this situation is what the study seems to be most interested in, admitting to binge drinking. Anyone see what the figure should be for P on this one? It wouldn't be the 244, not quite the 96. It wouldn't be the less than. It's really kind of tricky, right? And again, that's kind of why we focus so much on that very first example, example 1 in chapter 1, is because these matters are actually really, really tricky. Breaking down a study and deciding what is the right parameter, it takes time, but there are some hints on this. Recall that whenever you think parameter, you're thinking about a number associated with a population. Then back down here, what is the population? Well, they said there's a national result. I was talking about everybody in the nation. So apparently the population in this would be everybody in the United States of America. So now when they said a national result of 44%, we are describing the population right here. So let's say, just as a note, describes. Let me make that a little bit easier to read. Describes the population. And that's what makes it a parameter. So the parameter in this problem would be, we go to decimal form, 0.44. So 44% of the people admitted to binge drinking gave us this parameter value. Again, we don't know if it's exactly equal to 0.44, but it was the result for the national data. But there's another part of this drama right here. We were refining our population to something smaller, just a university. So the sample came from a smaller population, and the purpose of this problem is now to compare what's going on in the university with the entire national result. So when the sample of 244 came up, this was the sample size, n is 244. But that gets rolled into the statistic up here. The sample's proportion of successes just goes down into the denominator. A success is the part of the problem you're studying, admitting to binge drinking, and they said 96 of them admitted to binge drinking. So we can put all that together, describe the sample of 244 students at this university, and say the statistic is P hat. P hat is going to be number of successes, 96 of them, divide by the sample size n, 244. And that parameter, excuse me, that statistic value P hat right here is just fine the way it is. Let's compute it just for the sake of comparison. 96 divided by 244 comes out as a 0.3934. And it would be at this point, the university administrator would probably announce to the whole campus, we're doing great. Look at how lower this is in the national value. But that's not actually accurate. This could get the university administrator in some hot water, because in statistics, it had a lot to do with the sampling. We selected a sample of 244 students. A different sample could give us a whole different value here. It could be above 0.44. We need inferential statistics to tell us, is that figure, the statistic, significantly different from this value that was just dropped on us? But the major takeaway also is it's tough to define the parameter in the statistic. And this was just our second kind of look at it. in these notes here, where we're looking more at categorical data. Example 1 in chapter 1 was our first look at it when we were dealing with quantitative data, so all of this stuff. Well, any last questions at all, folks, with the rundown of example 1? Okay, sorry for going past the minute. That's a bad habit of mine. My hope was to get to this diagram. We'll come back to this after we take questions on Thursday relative to exam 1. But I'll leave this for you to take a look at and consider. This is a good one to stare at a lot, because this is trying to tell you what is really going on with the central limit theorem. And it is pretty abstract in my opinion, but we're definitely over time. If you have any questions, I'll be happy to address them. So feel free to stick around. Otherwise, I'll see you all in Thursday's class. Take care, folks.
Thank you.
Yep, take care. Yep, take care, Hayes.